Welcome. Today we're going to talk about autoencoders as well as variational autoencoders. Autoencoders are conceptually simpler, so we're going to cover them first and get to variational autoencoders or VAEs afterwards. So autoencoders. Autoencoders can be seen as a sort of compression of an input and then a decompression of the input. Let's try to be a bit more precise. So what we have with an autoencoder is we're going to have, first of all, an input. The input is going to be represented as, say, x, which is in some RD. Then we're going to have what's known as an encoder, which is a function which maps from r to the d to some other dimension, r to the m. We're going to have a decoder, which maps from r to the m to r to the d. So you can see we start with some input dimension, and then we take our input, we can map it to some other dimension, and then we map from that original dimension back to the original dimension. So you can see how the dimension changes and goes back. And our goal is to output that g of f of x is equal to x. That is, we want it such that for any x we feed it, that we're essentially the ones who are going to be optimizing this f and this g. They're going to be surprise neural networks. So we essentially have to construct some neural networks which take whatever input we give it, and then it encodes it, and then it decodes it, and then returns the same thing again. Now you might be thinking, this is really silly. This is in fact really easy, right? Because if we don't need to do anything, then just let if m is equal to d, then all we have to do is let f of x be equal to x, and we can let g of z be equal to z. We'll just do the same symbol, g of x be equal to x. And so these are basically just the identity, and then we're done, because you just apply them both and it'll leave you back where you started. Now, of course, this is not interesting here, but the interesting case comes up when you have that m is much less than d. Why is that? Well, say for example, like just as an example, pretend say d is equal to 1000, so it's a moderately high dimensional image, or input, let's say, not necessarily an image, but m equals 10. So the idea is we have some sort of bottleneck in the network, or in the function. So let me just try to give you an image of what this broadly generically looks like. Here is an image which is from a post by Francois Chollet, which I link in the on the website. But you can see here, this is the kind of image of what you think should be going on. There's some sort of original input, and you feed into some encoder. So you can see this has a lot of pixels. This is a relatively high dimensional, comparatively high dimensional input, but it does some encoding and it compresses it down to some sort of lower dimensional encoding. So you can see here that this just has 10 pixels. So this went from 784 pixels down to 10 pixels, and then the decoder, it converts these 10 pixels back into the original input that we had. So you'll note that it's not the exact same as the original. This is maybe a bit sharper, this is a little bit blurrier, but in fact you can see that what it's trying to convey is the fact that you start with a higher dimensional image, we compress it down to some low dimensional representation, and then we undid that by taking it back to roughly the original image. That's essentially what autoencoders are. Right, a type of compression which compresses it down to a lower dimensional space. And we're going to see a few, we'll get a bit more into details. We'll start with something fairly simple, which are linear autoencoders. this is something like the following. So imagine we have some input, which is d-dimensional. And just pretend all these connections are here and say this is w sub f, these weights here. And then over here you have something which is in the original dimensional space, and connect it all up. Something like that. I mean, connect all edges, yeah. So you can see, and this is, say, WG, these edges here. So this is a simple linear one. Like this time explicitly, I'm going to say that there's no activation functions here. And in fact, the output is equal to, well, the input is going to be x, so you put it over here, and then you feed it through WF, so the thing here will be WF times x, and then the result here will be WG times that, so it's WG times WF times x, and that's the output here. Now, the important thing to note here is, see this middle layer. Notice how the input and the output are the same dimension, which is much higher than the intermediate representation's dimensionality. We went from 5 to 2 back to 5. So this, like I said, is called the bottleneck. And this is kind of where the input is perhaps most compressed. It kind of compresses whatever high dimensional input we have down to its most concise representation that we can do with only these two dimensions. So yeah, hopefully that's intuitive. And the idea is we're trying to get that this output WGWF times x to be approximately equal to x. That's our goal. Now, how do we do that? How do we actually optimize that? That's informal. Well, our objective, the loss function that we're going to try to optimize, is going to be a minimization over WF, WG, say summation over I of 1/2. It's basically going to be the L2 norm of the difference. The L2 norm squared, rather. The squared error is a pretty common one. We've used it many times, but you just use this as your loss function for a single point. So you can see that you're essentially wanting each point that we feed in to roughly match the encoded then decoded version of itself. And yeah, we use L2 norm squared as the error. And we can optimize this as usual, just do gradient descent or whatever other gradient-like method that we use. Yeah, this is relatively easy in this case because of the fact that it's totally linear. In fact, yeah, I guess you should be able to, I'd have to think about it, but you should be able to, I think, just optimize this using a least squares type solution. Anyway, so yeah, you can think of, like, the way essentially you can think of it also is that WF of x is a compression of x. It's an alternate representation in a lower dimensional space. I'll comment that when we're talking about linear autoencoders actually very closely correspond, not exactly the same, but very close to something known as principal component analysis. Or you might have heard of this as PCA. And this can also be seen as another type of compression or dimension reduction technique for data. And I'll just draw you a sketch as to what it essentially tries to do. Imagine you have some sort of data set, but I'm just going to draw it in 2 dimensions because I can't draw in more dimensions. And say your data set looks something like this, rather skewed, I guess, is the way to picture it. Well, the idea is what PCA will do is find the most interesting directions in which the data lies. So for example, you can see here, perhaps the most interesting direction can be defined as the one where the variance is highest in that direction. So that's kind of this direction here. If you project onto this red line here, you'll note that this is the direction which kind of maximizes the variance of the points in this 1D direction. So that gives us something that looks like this, where it's kind of, yeah, well separated. And so, yeah, that's, I guess if you wanted to convert back, suppose you just did this projection and you converted back, well, then it would look like, oh, I mean, yeah, I'm not going to try to draw it, but essentially it would be like you looked at this picture here, but then you projected each of these black dots onto the red line at the closest point. So you can see that doing this type of PCA here is very similar to, it's essentially finding the one direction which is most interesting and useful. And that's somewhat similar to what we're doing here. We're just finding a subset, a projection of our data in some sense, which is most interesting or useful or captures most of the energy, as it's sometimes said. Yeah, so that is just a vanilla autoencoder. Let's see, or sorry, not, yeah, just a vanilla autoencoder and linear autoencoder. There's, of course, say other variations, which are very common. For example, you might expect nonlinear autoencoders are also relevant. And this is just going to be essentially the same thing where F, G are nonlinear is the only difference. And the picture, okay, I'll draw it again, but say it'll look something like, keep it simple. Say something like this, but then I'm just going to explicitly draw the nonlinearities this time. I probably won't in the future. Say something like this, and then we decode. Yeah, something like this, and we have some nonlinearities here. And we output, yeah, some different potentially different nonlinearities here, whatever you want. And yeah, this is our nonlinear autoencoder. So yeah, this is more conceptual, more expressive than before, because of course we know that adding nonlinearities for neural networks generally makes them more expressive. They can capture more different functions, but conceptually they're not really too much different. So I'm not gonna really say too much more about those. I guess let me just write the loss function again. I guess we want to minimize over, say, WF, WG, where those are, say, like the weight matrices here. Of the exact same thing as before, essentially. G of F of X minus X, Xi, L2 norm squared. So this essentially says just, do the exact same thing as before. The F and the G, the only reason I write them this way instead of just WF is because they also, F and G also capture these nonlinearities that we're applying. Good. What else can we do? Well, we can also do say, deep autoencoders, which maybe you can picture what they're going to be. We just stack more layers. Yeah, maybe something like, I'm not going to draw the nonlinearities anymore. It was just illustrating at that time. But maybe we do something like this. And this is the encoder part. And then we maybe make it bigger again. Something like this. So this is a deeper autoencoder. Again, it's basically the same idea as all these other things we've looked at, but making it deeper can lead to it being more expressive again. Especially in practice. So these are all have been somewhat similar so far. There's some more interesting things that we can do, which are actually a little bit different. In terms of like, okay, we can make an image smaller dimensional and then make it bigger dimensional again, but can we learn anything more interesting about our data and what it looks like? And one thing that's useful for that is a sparse autoencoder. And the idea here is it tries to learn a particularly interesting representation of the data, which is does there exist one which is sparse, that is, it has mostly zeros or just only a few non-zero values. So for example, let's just do a simple one. So imagine we have something like this, and actually our so-called bottleneck layer in sparse autoencoders are sometimes even wider than they would be wider than the input. This will still be interesting due to the type of objective function we use. So yeah, something like this. And this time, our loss function is going to be more like the following. It will still be the same first part, g of f of xi minus xi in L2 norm squared. But then what we're also going to do is have a type of regularization penalty of f of xi in L1 norm. Now this should look kind of familiar if you think back to the beginning of this course, where remember, when we wanted to penalize a linear regression solution in order to make the parameter vector be particularly sparse, that is, have mostly zeros, what we did was we did this L1 penalization in what's known as the lasso. Well, similarly here, what we're going to do is we're also going to penalize the L1 norm of this basically the encoding of the input. So what that'll mean is that it'll essentially result in the representation, whatever's here, having a lot of zeros, only a few ones. So yeah, this sort of means that f of xi will be sparse. Now, ideally, what we're really trying to do, in fact, is what we really want to optimize is something like this L0 norm, as it's called. It's kind of a misnomer because it's not really, but yeah, the idea is here, if you do the L0 norm optimization, then this will what this means is count the number of non-zero entries here. That's what this zero norm means. It's equal to the number of non-zero entries in this vector. Now, you can't actually optimize that because it's not convex, so instead we use L1 norm as a kind of proxy, and things generally work out nonetheless. So yeah, that's a sparse autoencoder, and it looks for sparse representations in this middle layer. And the last type of autoencoder that we're going to talk about before moving on to variational ones is going to be the denoising autoencoder. And these are useful, like in terms of actually having a real application, so to speak, in the sense that it's very clear why these are useful. So the idea is that suppose we have some noisy images. We're given noisy images, as we know that at test time we're going to be given noisy images into our data, as our data, and we want to somehow denoise them and produce the original images. So what we can do is, when we're training, what we can do is prepare the autoencoder, the denoising autoencoder, to receive in noised images, and then we should have it reconstruct the original image. So let me write that down. Given noised input x tilde, let's say, produce x as output. And what do I mean by that? Well, we're basically going to have a network which looks something like this. We have something where we feed in x tilde, and we go to some bottleneck layer, and then the idea is the output should be x. And our goal is to minimize, essentially. So yeah, let me give you a picture right now, just to sort of illustrate what you can picture going into and out of this. So here's an image again from, I believe, Francois Chollet's tutorial, which again I link. But you can imagine that this is the clean data set, what we have at, say, training time. And we want to be able to train a denoising autoencoder to essentially denoise inputs. So what we do is, given this data set at the bottom here, what we're going to do is we're actually going to noise the images ourselves manually. We're going to maybe add Gaussian noise or whatever noise we think we're going to see in our inputs. And instead of feeding in these pictures and trying to reconstruct these pictures as the input, like given these pictures as input to try to reconstruct the same thing as output. It's a little bit different in the sense that we're going to actually feed in these as the input. The X tildes are going to be our manually noised images, and we want them to, we're going to optimize the network in order for the pictures to be their denoised versions. So let's write this as a loss function. We're trying to minimize over WF, WG, where summation I equals 1 to n. This sort of function. So you can see that what we're trying to do is make it so that the so-called, in quotes, encoding and then decoding of the noise version of the image should be close to the unnoised version. And remember, when we're training it, what we just imagine is we have these only unnoised versions, but we can manually noise them for our training purposes. At test time, again, we just assume that we're given these noised images, and then we want to denoise them. So it's kind of, yeah. Hopefully that's clear. Yeah, and these are just another variation of autoencoders, and these are, like I said, perhaps the ones which are most immediately obviously useful in terms of what you can do with them. Okay, so in summary, an autoencoder is something which is given an input, it tries to reproduce the same thing as output. And what are these useful for? These are useful for, say, compression. You can imagine. When I say useful, I'm stretching the notion of the word in the sense that if you actually talk about file compression, then there's actually much better algorithms for file compression, which are even lossless, whereas this one is going to be lossy. So these aren't really the type of things you want to use as compression algorithms in general. These can sometimes be good, but they're better. But in the sense that essentially what you can even do is once you have trained one of these autoencoders, then you can split it up into two halves. One half will be the encoder part and one half will be the decoder part, and then you can use them separately. For example, if you wanted to compress all your data, then you would feed it one by one into this encoder part of the network and then save everything once in the smaller representation space. And then when you want to decompress it again, you just feed it through the second half, the decoder part. Yeah, so that's one thing you can do. You can think of it as a type of data compression, though it's not always the best. Another thing is that you can find interesting representations in the sense that, remember when we were talking about the sparse case, we're trying to understand what is a representation of our data that has very few non-zero entries. So this can sometimes be interesting or useful. Yeah, but generally, interesting things can come when you look at the representation space, where you map it to this lower D representation. And the final thing I'll mention is that this denoising application, of course, this is something that, and more generally, say, fixed transformations of your data, or maybe random transformations of your data. If you can sort of simulate what type of transformations of your data you expect to happen, then you can use an autoencoder, a denoising autoencoder, to basically undo that. Stuff like that. So yeah, what autoencoders at their heart really do, though, is they learn something about the structure of a data set, right? I mean, given this set of images, it essentially finds out what is these images. They each take 700, basically around almost 800 dimensions in order to be able to represent them. But this is really redundant. So somehow what a autoencoder does is it finds, okay, what say 10 dimensions, 10 dimensions is even pretty good for representing MNIST. What say 10 dimensions are useful in terms of representing this? What kind of 10 dimensions capture the heart of this data set? And that's, I think, a kind of interesting thing conceptually to understand the structure of a data set. But what it is not good at, or not useful for necessarily, at least in this sort of simple form, is in terms of generating images. Remember, or like learning the distribution over images. Remember that when we were talking about last class with generative models and mixtures of Gaussians, is we try to imagine that we're trying to understand something about the distribution from which a data point or our data set is generated, where it sort of implicitly comes from. Where do their data come from? That's kind of what we're trying to learn, because that's useful in terms of sometimes computing probabilities of how likely some data points or some events happen, but perhaps more importantly, in terms of, I don't know more importantly, but another common application is, say, generating more things from the data set. So I give you a bunch of numbers which are generated according to which people have drawn, like these MNIST photos, but can you generate, if you could generate new images, that'd be really cool, like images that nobody else has ever drawn before. And so, yeah, that's kind of what the goal is with generative modeling, at least one of the goals of generative modeling. So that's what variational autoencoders will allow us to do. But let's build our way up to there. Let's not just jump all the way to variational autoencoders. Let's talk about what our goal is with generative modeling. So at least for today, our goal will be essentially given the following, given say x1 through xn, which are generated according to some distribution d. This is our setup. And the idea is that, yeah, there's some distribution d which generates our data points. There's sort of stochastically generated IID from this. And can we somehow approximate this distribution? Like, can we estimate d in some way? Or maybe another thing, our eventual goal will be, can we generate more samples? So given x1 through xn, maybe we understand, oh, I kind of get what data from d looks like. Can we generate more things? So generate, say, xn plus 1, xn plus 2, ... so on, something like that. So that's kind of our goal. And yeah, while before we were looking at fairly simple d, in the sense that we were looking before last time at mixtures of Gaussians. So, but on the other hand, recall mixtures of Gaussians are relatively comparatively simple. Say you have a mixture of, say, 10 Gaussian distributions. Well, sampling from a single Gaussian is super easy. Sampling from a mixture of Gaussians is easy if you know the parameters, stuff like that. So relatively speaking, a mixture of Gaussians is not that complicated or expressive a distribution. But the thing is, generally probability distributions can be much more complicated. So let me just say D may be complex. Let's say just more so than a GMM, a Gaussian mixture model. So, for example, consider, like, for the example that we've been looking at so far is MNIST images. Say like D is the distribution of handwritten images. Like, suppose I want you to draw samples from where the distribution is the distribution of how humans draw numbers. Handwritten, not images, handwritten numbers. Right. Say, essentially, these are some samples from that distribution of numbers drawn by people. But this is a very complex distribution, right? It's not clear at all what this distribution looks like in this original high-dimensional space. Like, maybe there's some sort of high-dimensional picture that you can imagine where I'm going to draw a very poor caricature, but yeah, this is like a picture, and maybe over in this part of space there's some density over here where all the like zeros live because they look kind of similar, and then there's some density over here in some other part of space where all the twos live, and so on, stuff like that. So you can imagine this can be a kind of complex distribution, and it's even fairly simple images. Let's suppose I talked about something even more complicated, say CFAR10 or ImageNet images, which are very, very complicated looking pictures of various things. These are really hard to really understand what these broadly speaking look like in terms of distributions. it's not something I can easily understand. It's a very complicated distribution in a high-dimensional space. So it seems hopeless in order to actually just learn and estimate this D directly, right? That said, neural networks are incredibly powerful, and instead of we're going to somehow let our neural network do all the hard work. Yeah, let me take a step back. So D is a distribution of handwritten numbers, or even ImageNet. Like I said, it can be complex, and I'll just leave it at that. But the idea, the solution is use a neural network to do the work. And the main idea sort of is not the final idea, but it's the kind of one of the core ideas is that what we want to do is we can sample from other simpler distributions, and then given samples from simpler distributions, we can train a neural network to map it to this more complicated distribution space. So yeah, let's say like what distribution do we know and do we understand? Well, the kind of the simplest probability distribution that we can sample from is the Gaussian distribution. So we're going to draw a sample from N0I, the sort of identity covariance Gaussian, map it to a sample from D. Let's try to draw a caricature of what I mean by this. So this is going to be a kind of just a silly drawing of what it might look like. But here we have, say, Z, where Z is drawn according to N0 identity, and say Z is in R to the M, where M is going to be relatively lower dimensional. And then maybe we have something going on here, and then maybe we have some more layers like this. Something like this. And then this output here will be X. And then this X is sampled according to D, hopefully, where X is in R to the D. So yeah, the idea is that we're going to be able to train a neural network which will take in just Gaussian samples, and it'll map those Gaussian samples to samples from this distribution D. The reason we do this again is because D might be very complicated. So rather than trying to sample directly from D, which seems too complex to express, we instead sample from a simple distribution and map it to something like that. Let me draw a kind of caricature, another caricature. I've got a lot of caricatures for you. But what data over here will look like is it'll be, say, Gaussian. I'm just drawing a 2D picture here. So we have this nice Gaussian distribution on the left-hand side, where this is going to be the type of stuff we feed into this network. And the idea is that each of these points in this distribution, each of these samples here, will be mapped to points in some sort of higher dimensional space. Okay, I can't draw again higher than 2 dimensions, but maybe something like, it'll look a little bit like that picture I drew before, where this is like maybe a more expressive distribution. And the idea is, say, this sample here might be mapped to this point over here, where, say, if we zoom in on what this point looks like, this is actually, say, a picture of 1, and this point over here maybe is mapped over to this point here. And this point here, if we zoom in on it, maybe this is like an 8. So yeah, hopefully that makes sense. This is kind of a picture, and you can see that this is nice and Gaussian, and this is my very poor drawing of what MNIST might look in a higher dimensional setting. And all our network is going to do is try to convert from this low dimensional space to this higher dimensional space. Cool. So that shows how even if the distribution is complex to represent, we can do it using a neural network. Okay, I mean, I haven't shown you any pictures. I haven't showed you that this actually works, but just trust me, it'll work reasonably well. So again, suppose also that this were done in the sense that suppose we had some sort of neural network which could do this sort of mapping. Then generating new images from D, or new data points, they don't necessarily have to be images, from this distribution D would be super easy, because we can just sample a point from the Gaussian kind of prior, as one might call it. And if you sample a Gaussian and then feed it into this, then it'll map to a sample from D. So that gives us a way of fulfilling this type of goal that we wanted to do. We just sample a very simple distribution and then feed it through the network. So that's kind of the heart of the idea of what we're going to try to do. But the actual execution is that we are going to use an autoencoder-like idea, and we're going to use what's known as a variational autoencoder. And the difference between what's the difference between a variational autoencoder and an autoencoder? The primary difference between a VAE, let me just write this so that it's often called a VAE. The primary difference between an autoencoder and a VAE is the fact that while this is where it gets a little bit more abstract, while an autoencoder would compress things down to a lower dimensional representation, which is sort of another vector, what instead VAEs are going to do are they're going to work with probability distributions as our hidden representations. So that might sound a bit weird, but we're going to try to make it a little bit more concrete. But yeah, that's the main idea. Kind of, it's more probabilistic in terms of the representations of things. In particular, autoencoders by themselves, well, we didn't actually use any randomness at all when talking about these, right? You just feed something in, you try to find some representation. These were totally deterministic in their functionality. But however, variational autoencoders are kind of an inherently probabilistic object. So let's try to draw and explain as clearly as I can what's going on with a variational autoencoder, and what type of picture you should have in your head. So there's again going to be it's actually going to look kind of different from any other neural network you've seen so far, because of the fact that there's this odd probabilistic sampling step. So we'll see, but it's going to be a little bit weird. So yeah, the first thing we're going to have is our encoder. So here we're going to have x, which is in, say, r to the d. And this is going to somehow encode it. I'm just going to draw a single layer because that's simpler. And we're going to have a network which goes to something which is of width 2m here. So here we're going to have, say, these two nodes. We are going to call these u of x, which is in mu of x, which is in r to the m. And these ones here are going to be sigma of x to the rm. So you'll see we have two m parameters here. And this is the encoder. So this is a bit different than what we did before, in the sense that what we did before is we just mapped to some representation. What we're doing now is we're going to map to the parameters of a probability distribution representation. So the sort of hidden representation of any point will now be like a distribution, and these are the parameters of that distribution. So that's the encoder. And what is the decoder? This might, because you might be wondering, what do you do with this mu and the sigma? Well, this decoder, this is going to be over here. And what do we have here? The decoder. What we're going to have here is we're going to have some vector z, and the output is going to be, let's say z is in r to the m, and the output is going to be x tilde in, say, back to r to the d. And where does the z come from? You know, we have the big gap in our network here between the encoder and the decoder. Well, we're going to connect them via a sampling step. Remember, like I said, these are going to be the parameters of a distributional representation of x's encoding. So in fact, that encoding is going to be z. So let's see what z is. Z is going to be a sample from the distribution, which is like this, mu of x, comma, diag of sigma squared x. Yeah, and like I said, this is an R to the M. So now, what do we mean by this? What is going on here? Well, again, we take this MD vector and we treat the first half of the we treat this MD vector as the mean. And this other MD vector, what we're going to do is we are going to square it entry-wise in order to make it a set of variances. And then we're going to put it as diagonals in this covariance matrix. So this is going to essentially look like, this is going to look something like sigma squared x, and then 1, this is the first coordinate, and then you're going to have all the way up to sigma squared x, and then this is the mth coordinate, and then everything off the diagonal is going to be 0. And that's going to be your covariance matrix of this latent representation, as it's called. So yeah, this is, like I said, this is going to be a little bit funky. This is a bit odd for you maybe because of the fact that it's a neural network, but all the neural networks we've seen before are essentially deterministic. And yeah, the sampling step in the middle is what makes this a randomized procedure. Importantly, if you're really keen right now and you're very sharp, then you might have noticed that this is going to be really weird when we're doing optimization, right? In the sense, usually we've been doing some sort of back propagation, which consists for a bunch of like derivatives, but here it's not clear how we'll do that when we have the sampling step in the middle. So be aware that that's going to be an issue, but we're going to be able to deal with that with a neat, what's known as the Re-Parameterization trick. So this is our network here, and this is what it's going to look like, and this is what we're going to try to optimize. Yeah, hopefully at least the picture of what's going to be going on in the network makes vague sense. And let's talk more technical details in terms of it. Yeah, let's build up a little bit of notation, some notation. So what we're going to have is we're going to have to write a bit of notation. What we want is that p of theta of x. So this is essentially going to be the decoder network's density. So essentially you can think of theta as the parameters in this decoder network. So is density of decoder network. And you might be wondering, how is it a density in the sense like where's the sampling going to happen? Well, the idea is that we're going to be drawing some samples, and in the end it should be drawing samples from the density which corresponds to, like we said before, d. Our target is essentially that's going to be that p sub theta of x is going to be equal to this d. Now we're never going to be able to do exactly that, but that's kind of our goal, to approximate that as best we can. Some other important notation is the fact that what about this? We need p of theta of x given z. So what does this mean? It means essentially when we feed in a particular value of z here, then what value of x is going to come out the other side? And this is going to, in general, be a distribution. So this is a distribution over decoder's outputs. That's the same thing as we had before, given a fixed z. So that's kind of it's kind of, if you understand probability notation, then that's of course what this is. Yeah, so maybe nothing too surprising there. And the last thing that is important is p theta of z is what do I want to say, distribution over encoder's input. and we're using, and most people use, N0 identity. Let me elaborate on this a bit. The idea is that we really have the flexibility to choose what sort of distribution we want this this latent representation to come from. So let me take a step back. Remember, I said our goal really is to be able to start with samples from some simple distribution and map it to this more complex distribution. Well, like I said, we're going to use Gaussians as our simple distribution. That's kind of one of the canonical simple ones. But hypothetically, we could have used any sort of latent representation. This could have been any sort of other distribution that we know and like. But for mathematical convenience, Gaussians are going to kind of be the nicest one. So we're going to say that we picture that, yeah, if we want to generate points from P sub theta, if we want P sub theta to be a distribution over points from the real distribution D, then P sub theta of the Z on these these latent variables, that's going to be the Gaussian that we're going to try to enforce it to be, which is N0I. So good. That's most of the notation that was going to be useful for us. The last thing we're going to need is, we haven't talked at all about this encoder network here, this board thing, so let's give it a little bit of attention. And we have Q of phi. The one piece of notation we're going to use is Q phi of Z given X. And I'm not going to write what this is, but let me at least say what it is. This is the decoder's distribution over these latent vectors here, given a particular value of X. So essentially, all this is saying, this distribution here is what you get if you feed in an X, and you feed it through this network, and then you sample according to this sampling process, and that's the distribution you have here. That's exactly what Q is. It expresses that. So in fact, you can think of this phi here as being all the weights that happen in terms of generating these mu's and these sigmas. So yeah, it's a distribution over the latent vector given a particular input vector. And this distribution is sort of defined by the encoder network's parameters. Good. We're not going to worry, like you might be wondering, why aren't we considering Q of phi of Z or Q of phi of X? Well, those aren't really too important in our analysis in terms of what I'm going to write here. So cool. This is just some notation which we'll find useful. Okay, let's take another step sort of back up in terms of conceptually. So this is going to be our network, and what we really want to do is there's two objectives. I'm not going to derive. Okay, I'm not going to derive the objective function of a VAE formally for you. I'm going to point you to some references, but what I will do is try to motivate why it's a reasonable thing to do. There's kind of two things that we want to be able to do with a VAE simultaneously. One, remember, we want to be able to yeah, the first thing that we're trying to do is we're trying to really, what's the way to say this? Yeah, let me just, one thing we want to do is basically do the same thing we did with an autoencoder, which is essentially starting with some input X. We want that input X to be mapped to some particular Z. And then what we do is we map back to some X tilde, which is close to the original X. So the idea is we essentially want that this variational autoencoder will map points to something similar to what they were originally. So that's kind of the same thing as the encoder type desideratum. That's yeah, one thing, that it works kind of like an autoencoder, but with a little bit of syntactic sugar on top of it, because we're dealing with probability distributions here. The other thing we want is the fact that when we map a point, we want it to be mapped to this N0 identity, because like we said, we're going to kind of enforce that the decoder's distribution over this latent vector, we want that, we're going to sort of force that to be the identity covariance Gaussian, because that's what we're going to sample from. So therefore, if we're going to be sampling from this to generate new pictures or new output points, then we're going to want to try to constrain it so that the samples, that the things in the original dimensionality are being mapped to the Gaussian. So this might be a little bit abstract, but let's go back to this picture. So let me copy and paste this. Yeah, let's say this. So maybe the picture you should have, like when we just drew a kind of a generator, was or just the this just the decoder part was this. But what we actually want is the how you can actually picture it is something like this, where what we start with is samples from the original distribution, and what we do maybe is we map from points in the original space to things like this, and then we map back. Of course, it's all done kind of with probability distribution examples. So like the kind of corresponding to this right here, then this is going to be kind of the encoder operation, and this is going to be the decoder, and this is going to be, you can think of this as z, and this is x, and this is x tilde, x tilde, x hat, I think x tilde. Yeah, that's kind of the picture that you can think is going on. And yeah, like what I was saying is that we want to be able to make sure that our encoder maps from whatever odd distribution we have. We're going to try to make it so that it converts it into something that looks like a Gaussian, something nice like this. So right, those are our two essential things that we're going to want to simultaneously do when dealing with a VAE. One is make sure when you put it through the whole thing that it's going to produce essentially the same point as you had when you started. So that's essentially saying that this right here is going to be roughly the same as where we started. The other thing we want to do is make sure that the set of points, when we map them to when we start with the original distribution of points, that we essentially map it to a Gaussian. So those are two goals that we're going to have, and if we express those two goals mathematically, and then it will lead us to something that we can optimize. Okay, so I've been saying this a bit informally, but let me try to say the following. So our goals are ensure that input image distribution maps to N0I. And yeah, let me sort of draw this in blue. What this kind of means, like the fact that, say, these points go here and here and here, and that this overall distribution looks kind of like this. So that's maybe how you can think of that. And the other thing that we want is that let me say more mathematically how we're going to do this. What we're going to do is, or like what our objective, what term in the objective function is going to try to ensure this? Well, the way we do this more mathematically is we minimize what is known as the KL divergence, which I've mentioned in a previous lecture, between u phi of z given x respect to p of theta of z, which is equal to the KL of u of phi z given x respect to n0 identity. So, okay, what am I saying here? Recall that I mentioned before that KL divergence is a type of distance between probability distributions. So this is essentially saying how far these two quantities are from each other. And what are these two quantities? Well, let's take a look at this here. P of theta of z, like we said, that's just the probability distribution that we're trying to enforce on this latent vector z. And like we said, we're just going to try to make it a normal with zero mean and identity covariance. So that's why we substituted it in. Now, what is the other term here? Well, the other term here is the distribution of z, that is the latent vector, when x is sampled from the distribution of images. So when x is coming from the original distribution d, then this is kind of the distribution that we're trying to make approximately Gaussian. So yeah, essentially, just to sort of say that more succinctly, imagine we sample a point from the original distribution, and we map it using the encoder. Then we want this to be roughly the Gaussian with identity covariance. It's what I told you in words, but now converted into math. And this expression is something that we're going to be able to optimize. But we'll revisit that in a bit. Hopefully this makes sense why these two things correspond to each other. Ensure that this input distribution maps to N01 or N0I. That's sort of equivalent or done by minimizing this KL. Okay, the other thing is to the kind of autoencoder type of guarantee that we want, where, like I said, if you start with a point and then you map it into Z, and then you map back to the original domain, then it should be approximately equal to the original thing you started with. So let me sort of say inputs get encoded and then decoded to same. Decoded back. So yeah, I'll say it's kind of the autoencoder property. And the way we do this for a VAE is, like before, remember the way we ensured this was that we had like g of f of x is approximately equal, like minus x is and L2 norm squared is small. But this time what we're going to do is we're going to do something slightly different because we're dealing with probability distributions here. And it turns out the right thing to do is to maximize the following quantity. So, okay, what is this quantity? Let's take a look at it one by one. So first of all, the first thing we do is we sample Z from this distribution, Q sub phi of Z given X. So this essentially says that for some particular X, what we're going to do is we're going to feed it through this encoder network and do some sampling procedure to get some Z. So this essentially says that Z, this implicitly says that this random thing Z that we're drawing is some sort of probabilistic encoding of X. And then what we do is we feed this into the decoder network. So Z, our encoding, our probabilistic encoding of X is fed into Z. And what we're trying to do at this point is maximize the likelihood, essentially, of seeing the original point X again. We want to maximize the likelihood. It's kind of essentially a maximum likelihood type procedure. So this is at its heart saying that we recover. Yeah, this says that it assigns the maximum probability possible, or as much as we can, to the original point that came from. So hopefully that makes sense. Start with a point, feed it in through the network, and then at the end we want to maximize the probability that's generated again. It can't be like necessarily exactly the distance to the point, because remember we deal with probability distributions here, but we want to say that at least the probability of it is maximized. Okay, so those are the two types of things, and let's yeah, these are the two types of things that we're going to want to optimize. And in fact, the nice thing that we can say, okay, I guess I started doing this, but let me say that, yeah, like draw in orange what this kind of says. It kind of says that this whole process from here to here is going to be close to where it started, informally. But that's the caricature that you might be able to have in your head. Okay, so these are sort of two things intuitively that we'd like to optimize. And the claim that I'm going to make is, I'm not going to justify this claim, is the following. So the claim is, if you want to maximize, or let me just say it like this, the log of p of theta of x, this is going to be greater than, I mean, it's these two terms I just wrote, so this. And this. Okay, so this is my claim, like I said, which I am not going to justify. What this essentially says is that the log of the density of that the decoder network assigns to the particular point x is greater than these two terms which we just explored. And what does this actually mean operationally? It means if you want to maximize this term on the left, and we do want to maximize this term on the left, because remember, this is exactly what we're doing when we're doing maximum likelihood. When we're doing maximum likelihood, we just basically do a summation over the points in the training data set, and we try to make this as big as possible by choosing the parameters theta. Well, if we want to optimize this thing on the left, one way we can do that is optimize the thing on the right instead, because always less than or equal to, pushing this as big as possible will push this thing on the left as big as possible. Cool. So like I said, I'm not going to derive this, but there's many excellent resources, some of which I'll link on the website, which kind of derive where this comes from. It's not super hard. It's just, I don't think that illuminating, especially. It's not that illuminating if we do it very quickly. Okay. And let me note that you might think this actually looks a bit familiar. This is kind of related to the EM algorithm we saw in the previous lecture, in the sense that, you know, the kind of important thing is that before, on the left-hand side, what we care about is just the actual density of x, but what we introduce is these latent variables z, and the distribution somehow of these latent variables z is very important in terms of trying to optimize the likelihood of our data. So that's kind of there, and this is all these variational autoencoders are part of a more broad part of statistics known as variational inference. But I'll say nothing more about that, and this is just the buzzword you should look up if you are curious about learning more. So yeah, like that, let's just revisit I guess this expression and see how to optimize this. So let me just take this with us to the next page. So yeah, like I said, the way that we are going to optimize the thing on the left, the expression on the left will be optimized by instead optimizing the thing on the right. And again, the reason we want to optimize the thing on the left is due to the maximum likelihood principle, where we're really trying to find the most likely distribution that generated the data, or which could generate the data. So we'll do this by doing the thing on the right. And so we'll do this one term at a time. What do I mean by optimize one term at a time? Like, in terms of dealing with the gradient, let's explore the terms one at a time. So let's, for example, start by looking at this term on the right. So this one right here, this KL divergence. We haven't even talked much about KL divergence in this class, but the fortunate thing when we're dealing with KL divergence is the fact that we have some nice expressions for it. So first of all, let's expand this a little bit in the sense that this expression right here, well, we actually know what this distribution here looks like, right? Because Q of phi of z given x, well, we know what that's going to be. The distribution of z is going to be precisely this distribution. That is, it's going to be, z is going to be Q of this distribution. Q is going to be a Gaussian with this mean and variance, which is given by the parameters of this, by the outputs of this neural network. So we can actually write this right here. This is equal to KL of n, or Gaussian, mu of phi of x. I'm just saying mu sub phi of x because it's kind of implicitly with respect to the parameters of the encoder, and the covariance is, like I said, diag of sigma squared, where this is again entry-wise squaring because it's a vector of x. and close paren with respect to n0 identity. Yeah, we do the bars here. That's how we represent KL divergence. And the convenient thing is that when we're dealing with KL divergence, in some cases it can be complicated. But fortunately, when we're looking at KL divergence between two Gaussians, it's actually very simple. So I'm just going to write what it is. This KL divergence between these two Gaussians is equal to 1/2 times the following quantities. And this is going to be the jth coordinate of this vector. And close. So this is going to be the expression for the KL divergence of these two distributions right here. It might look a little bit complex, but it's not really that bad in the sense that these are just parameters which are output from the neural net, and you just feed them in to this expression here, and that's what your loss is going to be. Right? Somehow we started with distributions, but in terms of when you're actually optimizing the neural network, this is the term that's going to appear in your loss function, which is really just an expression of things which are deterministic quantities. So it's maybe not actually that bad as it might have seen from this crazy probability distribution type representation. And just for some sanity checks, by the way, remember I said it's a type of distance. So the distance between any sort of distribution and itself should be 0. So just as a sanity check, what if let's just say if mu phi equals x equals 0, and well, let's say if sigma squared phi of x sub j equals 1 for all j. So basically saying, what if this network outputs that the mean vector is equal to the 0 vector and the covariance is equal to just the identity? Well, in that case, you can see that what happens is that this will become, what will each of these terms become? Well, this term here will just be 0. Then this will be minus m. This will be a summation over, this will be just 1 because we're saying it's equal to 1 for every coordinate. And this will be minus log of 1, which is going to be 0. So we have 0 minus m plus m times 1, and overall this is going to be equal to 0 in this special case. So just as a brief sanity check, what we did was just showed that if you send in like the identity covariance 0 mean Gaussian, then the distance between these will be 0, and that's sort of how one could hypothetically minimize it. But more broadly speaking, it's not going to be exactly this, but it tries to get it close to it. So yeah, the goal of one of the terms that's going to appear in our final loss function is going to be exactly this expression here. Okay, so that is the one term which appears in our loss function. In fact, yeah, what do I want to say? In fact, it's going to appear negated, and we're going to try to maximize this minus this. Or it could appear positive, but then you'd have to negate this. But the point is, this is going to be here one of our terms in our optimization function. And we're going to want to minimize this. Yeah, okay, so this is one term. And the other term is the one which we're trying to look at here, which essentially says that a point, if we sample it and if we take a point and we put it through the encoder and then we decode it, then essentially we get something with which assigns a high likelihood to it. Well, this is actually going to be somewhat similar. So the other term is expectation of z from u phi of z given x. And then here we have log of p theta of x given z. Okay, an important thing I will mention here is for the sake of computing our loss function, what we're going to do is we're going to imagine that the output is that we're going to say that p of theta of x given z, this is going to be sampled according to n of mu of theta of x given z, and the identity covariance. So to elaborate on this, like, remember earlier when we were talking about where this hidden vector, this latent representation comes from? Well, this is a sample from a probability distribution with a parameter that came from the output here. Well, for the sake of computing the loss, what we're going to do is something similar here. We're going to take these outputs here and then sample, essentially, like, we're going to sample the point, I guess, x prime, which is drawn according to n mu of theta, where this is x given z, comma, identity. So we're essentially going to sample another probability distribution from this, or I guess we can put x tilde here. But the point is, you can picture this as a sampling procedure here in order to generate the point, but you don't actually have to do it, in the sense that really it's just we're just going to use the output, and the output of this is going to be our point. So this might be a little bit complicated, but think back to when we were talking about just standard vanilla neural networks, when we computed these logits. So that essentially tells us a probability distribution over the outputs, right? When we do the softmax, that gives us a vector, right? It gives us a probability distribution, say something like 0.7, 0.2, 0.1, something like that. So the idea when we did a softmax like that is that we were thinking that, we were thinking of this as a probability distribution, and the best prediction of what it should be is really the highest probability element from this vector. So in particular, when we're choosing which label to give, we choose whichever term is largest in the softmax. Now, on the other hand, we actually use this entire vector when we're computing the loss, though. So similarly, at this point, instead of at this point at the end of the network, what we're going to do when we're actually outputting a single thing, when we want to output a point, then we're just going to output the result itself, because that's going to be the mean, which is the most likely point under this distribution. But in terms of actually computing the loss function, then we're going to use this entire vector. So that is this entire distribution as a concept of what the output is. So hopefully that isn't too confusing, that we're picturing this output, that this p of theta being a distribution, even though we're just going to take just a single point. And again, this is kind of like akin to softmax, where we make a distribution over the outputs, but we don't actually necessarily sample from it. Okay, but again, if we assume that this is a Gaussian, well, now we're just doing we're just trying to compute the log of the PDF of a Gaussian, and this is very well understood in the sense that this is just going to be expectation, the sum u phi of the given x of, I'll write the expression here, something like this, minus d times log of square root 2 pi or something. So this is what we're going to be trying to optimize, because, like I said, this is going to be the other term in our expression, which we're going to try to maximize. So when we're trying to maximize this, note that this latter term is just a constant, so it will not be relevant. So we can just totally ignore that in our optimization. And all we have to do is optimize this. Now, this is finally where one of these issues that I sort of put a thumbtack in earlier rears its head, in the sense that in order to optimize this, again, we have to compute this expectation over z given this, and in order to optimize it, we actually have to do back propagation and compute derivatives through this expectation. Essentially, we have to take the derivative, and there's this like phi here, which is complicated in the sense that like we have to take the derivative with respect to these parameters, which appear in the expectation. So this just seems really weird and bizarre, right? Because how are we supposed to take a different derivative with respect to that? Well, the fortunate thing is we are going to basically, we're going to basically take this network here, and we're going to do what's known as the Re-Parameterization Trick. So what I'm going to do is I'm going to just let's take a look at this. I'll draw the key part of this component. This is known as the Reparameterization Trick. The idea is the following. So essentially what we had before is the following setup, mu and sigma. And what we do is that we draw z from Gaussian with mean mu and variance sigma squared, where this is right here, z. So this is kind of how I drew the network before, and it's not really clear how one would take a gradient with respect to this, because it has to kind of back propagate through the sampling operation. Seems kind of flaky, and I'm not sure how you do that. But it's not so bad if you do this reparameterization trick where you just draw it a different way. So what you do is now you're going to have mu here as before. You have sigma here as before. But now what you're going to have here is g, where g is drawn according to n 0 times 1. And what you do now is you can write the following. So you can kind of do this simple little network here. This is the times. And then you have here a plus. And this goes over here. And what happens if you multiply Gaussian by sigma? Well, this becomes n 0 sigma squared. And then when you add on the mu, this becomes n mu comma sigma squared. And this is equal to z, because it's the exact same sampling procedure. So you can see what we did here was we kind of wrote this in a different way, which at least looks a little bit nicer, right? Because now at least this looks like a simple neural network type setup here. So maybe we can do something here. And indeed, we can do something. At least this allows us to do back propagation in terms of getting the gradients for with respect to these parameters mu and sigma, and these will back propagate through the rest of, when you're doing back propagation, you also compute the gradients and go through the rest of the network all the way back to the inputs. But the most important thing is that we got rid of really the sampling step here, which we didn't have to deal with. So what happens here when we do the back propagation, now we're going to go through here and we don't have to go through the sampling. We're still going to have to deal with the sampling operation in the sense that we still care about computing an expectation of this quantity. But the way we can do the expectation now is we can just compute, we can just draw samples from G, and we do many different samples and we can compute the gradient over all of them and then just average them. So this is now G is considered, basically G acts as an input to the network now, where it's our random noise. And by averaging over many realizations of this random noise, then we can actually compute or at least approximate this expectation. And generally doing it just approximately via this Monte Carlo method is good enough. So yeah, in short, this might have been a little bit odd, but let me try to summarize what we did here overall for variational autoencoders. What variational autoencoders are trying to solve is the problem of generative modeling, where we can generate samples from a probability distribution, which might be rather complex. And so the idea is we try to use a neural network in order to start with a more simple distribution, which we can represent and map to samples from this more complex distribution. And the way we do this is by using a variational autoencoder. What our variational autoencoder does is it first maps, it simultaneously tries to do two things. One, it tries to map its original distribution to a distribution which is Gaussian, and then maps from that Gaussian N0 identity distribution back to the original thing. Yeah, that's the main goal that it tries to do. And there's kind of two things here that we care about. One is mapping back to really the original distribution, and also in the middle, mapping to the Gaussian distribution. So those two different goals are what show up in our loss function. We want to ensure that the input image maps to the Gaussian N0I. And the other thing we want to do simultaneously, ensure that inputs get encoded then decoded back to the original thing. So those are the two goals, and those are two terms which appear in our loss function. So what we could do then with these two terms that appear in our loss function, we could simplify them just based on things we know about our network, and using properties of Gaussians and expressions for KL divergence and stuff like that. And they give us these nice two terms here, which are not really too complicated in the end. And then the last challenge we had to deal with was the fact that we have the sampling process in the middle of the network, and we can get around that by doing this Reparameterization trick, which treats the sampling step as an input rather than something which happens in the middle of the network. And that makes it nice for back propagation. And then additionally, we can deal with computing this expectation just by sampling a few samples from the this now with an input. Yeah, and that's basically VAEs in a nutshell. One thing I forgot to mention is you'll notice that here, this is actually, interestingly, this is the L2 norm between the point that we cared about and the encoding of the point we cared about. So this is essentially, if you think way back to when we started, this is just the L2 distance, the mean squared error between a point and its the reconstruction of a point. So it's essentially, despite this more complicated setup, it's the same thing we had before, which is kind of nice. So, okay, I've shown you all of this stuff in terms of how a VAE works. Now, what does a VAE actually do? Can it give you something cool? And yes, it can. Here are some pictures, which are from one of the original VAE papers by Kingma and Welling. So you can see here, these are what samples look like from a VAE. So okay, let me just, maybe this has been clear, but let me just make it totally explicit. How do we sample new images from a VAE? Well, the way we sample new images is we essentially throw out this encoder. We don't care about the encoder anymore if we just want to generate images. It's kind of useful for training. But once we have the decoder, we can throw out the encoder. And what we can do is feed in Gaussian noise to this decoder. And then if you feed in Gaussian inputs, then the outputs will be samples from the distribution. And that's what we're seeing here. We're seeing samples from the distribution, which is the mapping of Gaussian noise. And you can see on the left, this is what happens if you have a 2D latent space. That is, Z is only two-dimensional. And you can see these are pretty good pictures, though they're a little bit blurry. And as you increase the dimensionality of this latent space, you can see that they become sharper and sharper in general. There's still some kind of very questionable images here, which don't really look much like numbers. But generally, these look pretty numerical, so this is not bad. Yeah, one can even argue, in fact, that some of the 2D latent space stuff looks better than the higher dimensional latent space. Like this doesn't really look like a number, for example, but most of these do, I guess. And the very interesting thing, I think, one of the beautiful things about these variational autoencoders is that they actually let you see how the distribution can interpolate between one image and another. So for example, here is another figure from the same paper, which shows essentially an exploration by gridding over the latent space. That is, imagine this looking at this 2D version. So imagine that this vector Z is two-dimensional. And rather than drawing samples from that 2D space, imagine that instead you just took every point in that 2D space and then plotted them, you took every point in that 2D space, you fed them into the decoder network, and you plotted what the results were, and you get something like this. So you can see for certain points in the latent space, like you can see how the sort of images correspond and morph to each other. You can see the 7 slowly becomes a 1, and as you go here, it goes and turns into a 6, and then the 6 turns into an 8, and a 3, and so on. So this is kind of, I think this is really interesting, and it shows you how somehow the latent space can map to pictures that, and you can kind of interpolate between images in that way. Yeah, just by sort of interpolating in the latent space. Is there more I want to say about that? I mean, okay, let me try to say one more thing about that, just to hammer that home. Let's look at this picture that I drew here, and recall the idea here that we first took images and mapped them into this latent space Z. Well, the cool thing is, if you map into some latent space Z, and then you follow the line that connects one point to another, and you sort of map all of those things. Sorry, let me think of the best way to say this. Okay, here's what I'm going to say. Start with 2 images in the original space, and I'm going to tell you and explain how you can interpolate from one image and turn it into the other one in a sort of smooth-ish way. Well, the way that you would do this is first take those 2 images, map them into the latent space, latent distributional space, and then given those 2 points there, draw the line between them, draw the line connecting them, and then that line that connects those 2 points in the latent space, convert every point on that line and decode it again. Now, if you take the resulting set of decoded points, it'll nicely interpolate between one of those images and the one at the opposite end, and it'll be kind of smooth in terms of its conversion. That's maybe where you've seen a lot of these, potentially you've seen pictures of like GANs, which we'll talk about next time, and shows you one image changing to another, and that's kind of just exploring this latent space in that type of way. Yeah, this is at Variational Autoencoder. They're not necessarily the state of the art in terms of like generative models, but they're quite a nice idea. So I hope you got something out of them.